Hello everybody, this is Mr. Boston. We're going to do an energy conservation problem. It's going to involve a spring and compressing a ball into it, letting go and see how far it goes up. Let's read the problem and go ahead and give it a go. A 5 kilogram medicine ball is compressed half a meter into a vertical spring that has a stiffness of 400 newtons per meter. The ball is then released from this compressed position. How far upwards does the ball travel from this compressed position? Okay, so let's go ahead, and our first order of business is to identify what facts we have to work with. I see a kilogram, so this is a mass. I see compressed, so I'm going to say this is my maybe initial compression, and from this resting position of the spring, we're going to push it down this initial compression to this position. Okay, into vertical spring, its stiffness, this is the spring constant, lowercase k, and is released from this compressed position. I think our initial velocity is going to be 0 when we release it. How far upwards? That's going to be like a final height that we're looking for. Okay, so let's just look at a couple things here. So this is going to be our mass that we're going to shoot upwards. And when we release this mass, it's going to go up to a final height, a maximum height. At a maximum height, it's not going up anymore and it hasn't started going down yet. So it's going to stop for a moment in time. We're going to say this is our height we'd like to solve for. Okay, and I believe we're going to set this ball's lowest position as our initial height, and it's going to be equal to 0, and that's how I like to structure my problems. The lowest point for my problem I like to put as 0, so I can get rid of the energy, the gravitational energy, potential energy there, and I can only be measuring in the positive direction for stuff, so that's how I like to structure my problems. And that's pretty good. What's our system going to be? Let's think about that for a second. So I'm going to choose the ball. I have a spring, so I'm going to include the spring. And I'm going to have potential energy height changes, so I'm going to include the earth. So it's going to be the ball, the spring, and the earth is going to be my system. Okay, so let's go ahead and for our next little topic here, let's figure out what kind of energy transformations we're going to have. So initially, since this is my 0 height, it's going to be all spring energy or elastic energy. By the time it gets up to this, the ball comes off this spring and the spring isn't compressed anymore, well, it's going to be going quite fast. I'm going to have a lot of kinetic energy, but it's also raised its height a little bit, so I'm going to have a little bit of UG. About halfway up, it's going to be less kinetic energy, and it's going to be more gravitational potential energy. And by the time it gets to the very top, it's actually going to stop, and all that kinetic energy has transferred into UG. And so we have this energy transformation as this ball goes higher and higher. It starts as all spring, it ends up being some kinetic and some UG, and that eventually transfers to all UG. And so it's really important to be able to identify the energy transformations. Now, where did the energy come from for this thing to reach this height? Well, we did some work right here to compress it down. But once we had it compressed, we had all that energy as spring energy, and when we let go, it transferred over to this. So once we have it compressed and I let go, this is now going to be an isolated system. The energy we have in our system is going to be maintained. And so this is an isolated system. We can go ahead and work on making an equation for this. So let's check that out. So we're going to use energy conservation. And so my final energy, how I get my final energy depends on where I started what kind of energy I started with, plus how I changed my energy. And so this is the conservation of energy equation. We're saying it's isolated, so we don't have any work. Once we have it compressed, it's going to be an isolated system. The energy is going to be maintained in our system. And I can go ahead and start adding in the details for this. So my initial energies were going to be spring potential energy, and then that totally transferred eventually into gravitational potential energy. And I guess I'm skipping ahead a little bit right here. Why am I choosing these 2 points for my energy equation? Well, I'm never really told the speeds along here. And so I want to avoid adding more unknowns into my energy conservation equation than I necessarily need. I know everything about how it starts down here. I know everything about this. And I would like to solve for the height it reaches. So I'm going to make an equation that uses as much known information I can. I'm going to avoid using these points in here because I'm just not told anything about the speeds it has there. And I'm going to include this part, the top, because that has the information I want to solve for. So I'm going to avoid the stuff in between. And when we do energy conservation, we're only going to choose 2 points in time to consider. And I'm doing someplace I know everything about and someplace I would like to solve for. All right, so let's go ahead and add some detail in here. So our spring potential energy is going to be 1/2 K initial compression. All that energy turns into MGH stuff. And we would like to know what this H is right here. So let's go ahead and isolate for it. That is going to give us an equation that says KX squared divided by 2mg. And this is a fully descriptive equation for this scenario for what I need to do to maximize the height. This shows you everything all the dials you can turn and twist to manipulate your height of this ball when it gets launched off a spring. So the stiffer the spring, the higher the ball will tend to go. Okay, so the more powerful spring will launch it better. The more I compress the spring, the higher it will go. But the more massive the ball is that I launch, the lower it will tend to be. So if I launch a golf ball compared to a bowling ball, well, the bowling ball is not going to go as high. And hope that makes sense. And if I launch this on the moon, it would tend to go higher because gravity is not going to pull it to a stop as quickly. So in like a computer science class, we would call this thing an algorithm. That's interesting. So we can really see exactly what controls the height out of this thing. Now let's go ahead and put in our numbers for this. So my H is going to be, 400 times a half divided by 2 times 5 times 9.8. And I showed the units here too. So let's go ahead and cancel out some units here. So I see that I'm going to have meters squared on top. So I can get rid of 2 on the bottom. And this is interesting. I have a Newton, which is a derived unit. So it's composed of smaller units. So a Newton is a force. And by F equals ma, I know a Newton is equal to a mass, a kilogram, times acceleration, meters per second squared. And then I can go ahead and cancel out that Newton. I can get rid of some kilograms. I can get rid of some seconds. I should be left with meters for height, and indeed, that's what I'm left with. And in the end, we get out of this thing something that looks like 1.02 meters. So that's our answer for this particular problem. So this is a pretty straightforward energy problem, a nice one to start with when you're trying to learn how to use conservation of energy. It was an isolated system, so we didn't have any work. And so that meant our initial energy, and once we had the spring loaded up, should equal my final energy. And we saw that's our elastic energy turned into all potential energy. Um, okay, and the last thing I'd like to do for this is just to, I like to think about what happened to the energy transformations and try to visualize that. So we're going to do an energy bar chart. Let's get that set up. Okay, and so when I look at what those two energies were, my spring energy, I plug in all the stuff, and I got 50 joules. So I got 50 joules when I plugged in all the stuff for spring energy, and when I plugged in the stuff for, I took our answer and I plugged it back in for UG, I also got 50 joules, which should make sense because our energy was conserved, and there's our final should equal our initial, and there's only two types of energy involved with those 2 points. And we can go ahead and graph this. And so our initial energy was spring stuff, so we had 50 there. We didn't have any work. We didn't have any initial kinetic energy. We didn't have any initial gravitational. At the top, we didn't have any kinetic. We didn't have any thermal energy generated. Our spring was compressed. Therefore, all of this energy transferred neatly into 50 joules of gravitational potential energy. So you can see uh, this changed into this. So we're just plugging in for a bar chart. Hey, how did we end up with our final energy? It depends on how we started plus how we changed. That equals how you end up. Okay, so hopefully this is a good visualization and practice problem introducing how you do conservation of energy for springs involving a change in gravitational potential energy. Thanks.